Hello everyone, welcome to Physics 205. So in this video, I want to work out the solutions to the vector practice where you add vectors analytically. Okay, so this first question says, the figure below shows the forces acting on a sprinter in the set position of a sprint start. Given that force P, which looks like it's on the right foot here, is 210.7 newtons and acting at 40.6 degrees. Force Q, which is acting on the left foot, is 181.3 newtons at 63.1 degrees. Then the L and R, these two vectors are acting on the two hands. They're 228.34 newtons. They're both the same at 122 degrees. And then you have the weight of the person acting at their center of mass, acting down, 686 newtons at 270 degrees. So basically what we want to do is we want to add those 5 force vectors together to get a resultant vector. Now, it turns out because this person is static, right? They're just in this sprint set position, ready to start the race. They haven't started it yet. Then we should find that the net force acting on the person, if they're in a static position like this, should be 0, right? Or something very close to 0 within rounding error. So hopefully we'll end up getting something very close to 0 when we work this out. Okay, so in order to add all these 5 vectors analytically, I first need to find the components, right, of each of the vectors. So let me let's draw these out. So I have P. This is in the first quadrant. We know the angle is 40.6 degrees. So this angle right here is 40.6 degrees. And we know that the magnitude of P, let's write it as P with no arrow over, it's 210.7 newtons. And we want to find the X component. So we want to find like Px and then the Y component. Py. Okay, the second vector, I'm going to draw all these out first. The second vector is also in the first quadrant. It's Q. The magnitude of Q was 181.3 newtons. This direction was 63.1 degrees. And we want to find the components. So we want to find Qx and then Qy. Okay, then we have L and R. They were at what was the angle? Let's see, 122 degrees, right? Which is going to be in the second quadrant. So if this angle is 122 degrees, then what we really want to find, we want the reference angle here, right? Because it's going to be easier to find the components. We know the reference angle. So if I do 180 minus 122, I'm going to get 58 degrees as the reference angle. So 58. And again, I want to find the X component. So this is like Lx, and then the Y component. Ly. And then R is exactly the same thing, right? Oh, and we also knew the magnitude, right? The magnitude of L was 228.34 newtons. And R was exactly the same thing. So it was in the same exact direction, same magnitude. So again, this is 122 degrees. But I'll just do the reference angle, which is 58 degrees. And then to find the components, we want the x component. So this is like Rx. And then the y component, Ry. And then finally, the weight vector, that one's acting straight down. We know the magnitude was 686 newtons, and it's straight down. So this angle, if you want, you could say this angle is 270 degrees, right? Okay, so normally what I do now is I extract out the right triangle, right, for each one, and then we can figure out the components by using trig. But just to save a little bit of work, let's try and do all this work in a table, okay? So it'll be a little quicker. So I'm going to make a table. Instead of using I hats and J hats, I'm just going to do this in a table. I have X component, Y component, and then my vectors are going to be P, Q, L, R, and W. And I want to add all those up. Remember, the purpose of this is to add them all up to get the resultant force, which I probably shouldn't call R, right? Because I already used R. I think I called it R in my notes. Let's just call it like, I'll call it like R net or something, the net force. Okay, so if you look at P, the X component, first of all, the X component is positive, right? Because it points to the right, and the Y component is positive. If I extract out this right triangle here, then the X component, as long as I use the reference angle, is going to involve cosine, and the Y component will involve sine, right? So this will save a little bit of time. You can think of it this as this X component is going to be 210, so it's positive 210.7 times cosine of 40.6 degrees. And that equals 159.98. It's newtons, but I'll leave out the units right now. And the Y component, I'm going to have 210.7 times sine of 40.6 degrees. And that equals positive 137.12. Okay, Q. So now that it looks like both components are positive, right? QX is positive, QY is positive. I'm using the reference angle, the 63.1. So I know X will involve cosine, Y will involve sine. So this is going to be 181.3 times cosine of 63.1 degrees. That's going to be 82.03. And then it'll be 181.3 times sine of 63.1 degrees, which is going to be 161.68. Again, these are all newtons, right? I'll just put N here, newtons. Okay, what about L and R, right? These are going to be the same, L and R. Well, now you have to be a little careful. The X component is negative, right? It's pointing to, but the Y component is positive. And again, I'm going to use this right triangle here. I'll extract that one so that I can use this reference angle, which is 58 degrees. Again, why am I using that reference angle? Because I know the X component will just involve that reference angle, right? And the Y component will involve, so the X component will involve cosine of that reference angle, and the Y component will involve sine. But the X component is going to be negative, right? So it'll be negative 228.34 times cosine of 58 degrees. And that'll be negative 121. And then for the Y component, it's positive. It'll be 228.34 times sine of 58 degrees. And that's going to be 193.64. And then R is exactly the same, right? The forces that are exerted on the left and right hands are exactly the same in this case. So negative 121, and then this will be 193.64. And then finally, W, remember, if you look at W, it's pointing straight down. So the X component, none of that vector is in the X direction. The X component is 0. And the Y component will be negative the full amount, right? It'll be negative 686. So X component is 0 and negative, the Y component will be negative 686. Okay, so if I want to find the net force, R net, I have to add all these together, right? That's P plus Q plus L plus R plus W. But what does that mean to add the vectors? Well, analytically, it means add the components. And so I have a nice table here. If I just add down this column, right? These are the X components. If I add all these values together, that's going to be the X component of my net force. If I add this column together, these are going to be, it's going to be the Y component of my net force. So if you do this, you're going to get something very close to 0. In fact, we'll say it's approximately 0. And if I add the y's together, I'm going to get like 0.08, but that's just rounding error. This is very close to 0. So it turns out in this case that R net is going to be like 0 I hat plus 0 j hat. It's in newtons, right? In newtons. Which is what we thought, right? This sprinter hasn't started racing yet. So all those forces should sum to 0 so that the swimmer can stay in that position without moving. And that's what we found. They sum to 0, which is exactly what we expected. Okay, the second question is right here. So now the sprinter is ready to start accelerating. No, actually, the sprinter is accelerating in this question. So in this question, they've left, right? They're leaving the starting blocks. So they're accelerating. So there has to be a net force that's accelerating the individual. And we want to find that net force. And in this case, there's only 3 forces acting. We have force P, force Q, and force W, right? The forces on the hands aren't acting anymore. Right, so now we should find some force which is causing the sprinter to accelerate. Okay, so I'm going to do the same thing for this one. So let's first find the components. Okay, I'll draw this out again. So now P has a magnitude of 470.4 newtons. There's an angle here of 28 degrees. And we want to find the X component and the Y component. And then if I do Q, it's also in the first quadrant, which is nice. So something like this, Q. It has a magnitude of 999.6 newtons. This angle is 51 degrees. And again, we want to find the component. So we want to find QX. So I'll project it onto the x-axis. This is QX. And project this onto the y-axis, QY. And then finally, W is just the weight of the individual. That's just acting straight down again, right? So in this case, W is acting straight down. And we know that magnitude is 686, right? 686 newtons, that's the weight of the person. And this angle is 290 degrees. No, 270, right? Straight down will be 270 degrees. Okay, so what I want to do is I want to find, now I guess I'll call it R. I want to find the resultant vector, which is P plus Q plus W. All right, Again, to save time, let's do this little table. I thought the table works out pretty well. So I have X component, Y component, and I have vector P, Q, W, and I ultimately want to find R, which is the sum of those. Okay, so for the X component, if this is my right triangle, and again, I'm using the reference angle, PX is positive, right? PY is positive. So that's also going to be positive. So to work this out, well, the magnitude is 470. Remember, as long as you use the reference angle, the X component will always involve cosine. So 470.4 times cosine of 28, that's 415.34 newtons. And then the Y component will be 470.4 times sine of 28 degrees. And it turns out to be 220.84 newtons. Okay, Q, same thing. It's in the first quadrant, right? So it's going to be 999.6 times cosine of 51 degrees. That'll be positive 629.07 newtons. And then 999.6 times sine of 51 degrees. And that's going to be 776.84 newtons. And in the weight vector, just like before, there is no X component, right? None of it any X. And the Y is negative in the entire amount. So it's negative 686. Okay. By the way, you could use sines and cosines for this as well. If you do WX is the entire amount times cosine of 270, you're going to find that equals 0. And if you do WY is the entire amount times sine of 270, turns out sine of 270 is -1. You're going to find out you get negative 686. Okay, so you could actually use the 270, but if it's right along the axis, one of the axes, it's easier just to look at it and figure out what the components are. There's none of W's in the X direction, so that's got to be 0, and it's all in the negative Y. So the entire amount is in negative Y, so it's negative 686, which is much faster to do it that way. Okay, so now to find Rx here and Ry, I just add, right? I add down the columns. I add all my X values. I got PX, this is like PX, QX, WX, right? Add them together. If you do that, you're going to find that this is 1044.41. If I add the Y's together, I'm going to get 311.68 newtons. Okay, so that's my answer. If you want, you can write it in component form using I hat and J hat. So it's I hat plus 311.68 J hat newtons. Now, you may want to find the magnitude and direction of that vector. So that's the answer in component form. Let's also find the answer as a magnitude and direction. So to do that, right, let me draw this out. So I'll come over here. It looks like we're in the first quadrant, right? Because we're saying Rx is 1044.41, and then Ry is 311.68 newtons. So that means that vector R itself must be in that first quadrant. And we want to find the magnitude of R, and we want to find this angle theta. So if I extract out this right triangle here, this is 1044.4. This is 311.68, and I want to find R. So how do I do that? We've done this a bunch of times. I just need to use Pythagorean theorem, right? So I know that r is going to be the square root of 1044.4 squared plus 311.68 squared. I guess this is 4,1 here, 4,1. And if you work that out, r, the magnitude of r is going to be 1089.93. Probably don't have that many sig figs. Let me just do this to like, I'll say 1090, right, newtons. And then to figure out the angle, to get this angle theta, well, I know that tan of theta is opposite, so 311.68 divided by adjacent. So if I want to find theta, I need to do the inverse tan, right? So theta is going to be the inverse tan of opposite over adjacent. And if you work that out, you're going to find it's 16.6 degrees. Now, you don't even need to add anything else to it because we're in the first quadrant, but you could say like north of east just to make sure that the individual knows that you're in that first quadrant. So you either have it in component form like that, or I could write it as r is equal to 1089.9. Let me write it as 90. I'll round it a little bit. So 1090 newtons at 16.6 degrees. And I'll say north of east just to make sure we know that we're in that first quadrant. So either way, right? Either as component form or in polar form where I have a magnitude and a direction. So because I have this vector, this net force here, that means that this sprinter is going to accelerate. They will have an acceleration in the same direction as that force. Okay, which makes sense. They're accelerating out of the blocks here in the beginning of the sprint. Okay, whereas in the other case, they hadn't started yet, so that net force should have been 0. Right? That was the other problem. In this case, there is a net force, and it's at an angle of 16.6 degrees right above the horizontal. So they're accelerating in that direction. Okay, so those were a couple of examples on how to add vectors analytically. Great, thanks.